Hello everyone, my name is Philip Willamy and this is my car project. When I started the project, some things I knew I wanted to do were to use interrupts, to use the incremental rotary encoders to measure the speed and distance of the motors. I wanted to use all 4 sensors that came with the kit for positioning. I wanted to use a closed-loop digital control system, and I wanted to give myself performance feedback about how well the car was running. Here is the hardware block diagram. It shows the power supply and power regulator circuit as well as all the modules that were used in the project. This is how I wired up the power supply. I used wire clips to hold the loose wires, and I used collets for wires that run through the sheet metal on the car. This is my I/O map. The project used 22 MCU tower input and output pins connected to the Proto-Board. I connected general input and output pins by soldering header pins onto the Proto-Board. I used jumper wires to connect the header pins of the I/O to the header pins of the tower. The jumpers are removable, so the Proto-Board can be reused for other purposes, or the car can be changed to different pins if hardware is added or removed. For power and ground wires, I didn't use any jumpers. They're all soldered directly to the surface of the Proto-Board, and screw terminals are used to connect them to the board. This is an image of the finished construction. I cut a piece of plastic out to use for a cover for the tower, and I wrapped all the loose wires with wire wraps. This is how I positioned and set up the sensors. The weighted map is basically a Carnot map, and if the value of the sensors is less than 0, the line is under the passenger and the car should turn right. If the sensor's value is greater than 0, the line is under the driver and the car should turn left. If the sensors are equal to 0, the line is in the middle and the car should go straight. This is a screenshot of the oscilloscope capture of the SA and SB pulses used to record the motor speed and direction. The SA pins were connected to the MCU and trigger an interrupt. The incremental rotary encoder was used to measure the distance the car went and turn the car off after 2 laps. The theory of operation for the car is the user has the choice of 3 different controllers to use: a bang-bang controller, a PID controller, a fuzzy logic controller. Chapter 13 of the text covers these controllers in detail. In the bang-bang controller, the sensors trigger an interrupt service routine that reduces the motor speed, causing a sudden large change in the output of the pulse width modulator for a small change in the input sensors. PID controllers are widely used in industry to control systems. The PID controller is the sum of the proportional term, the integral term, and the derivative. The P is the difference between where you want to be and where you are. It's equivalent to the error in the system. The integral term is the accumulative error over time, and the derivative term is the change in error over time. Fuzzy logic controllers are commonly used for artificial intelligence, and they try and simulate how a human would control the car. Fuzzy logic controllers use error thresholds that are defined by the user, and it is the point where the car will determine if it is definitely out of position. For example, if I set the threshold for negative TE to negative 60 and the actual error is negative 53, the controller will determine it is a little to the left, but not all the way to the left. The user can set the threshold for direction similar to the threshold for error. The controller will then use both sets of information to determine what to do. If the error is large and the change in direction is large, then it will slow way down. If the error is small and the change in direction is small, it'll slow down a little. If the error is 0, then it'll go full speed. I used a USB to serial cable to connect to the car's SCI module to transmit and receive information between the car and the PC. I used a graphical user interface on my PC to communicate with the car's microprocessor. The radio button selects the steering algorithm. The slider and speedometer adjust the speed. Spin controllers adjust the PID variables and fuzzy logic thresholds. This information is transmitted to the car. The graphical user interface also receives performance data and saves the data in a file and displays a graph of key factors. It uses a checksum to verify data sent to the microcontroller. The fuzzy logic parameters are transmitted to the car. The fuzzy logic controller had the most interesting pulse width modulation and was overall the best controller. It consistently had the fastest lap times. Its best recorded time was 29.815 seconds. The GUI receives data from the car. The graph shows total distance traveled by both passenger and driver motors, amount of time it took to go 2 laps, and pulse width modulation of the sample intervals. The bang-bang parameters are transmitted to the car. The bang-bang controller had the second best recorded time, and it used the fewest resources. You can see by the pulse width modulation output why this is called a bang-bang controller. The pulse width modulation jumps back and forth between full on and full off. The PID controller had the slowest recorded time. This was largely due to saturation at the beginning of the cycle. With only 4 sensors, there isn't enough feedback to measure the error with accuracy. It's interesting to see the effect of the integral on the pulse width modulation output, and maybe if there was more time, the performance would increase. Some problems I encountered in the car project were chatter coming from the PEG, causing a lot of noise in the system. I could see the noise on the pulse width modulation data output. If the chatter got really bad, the car would steer out of control, and this was my primary speed limiting factor. The other problem I encountered was the inductor that was provided with the kit had 130 ohms of resistance and was dropping about 1.5 volts across it. So I removed the inductor from the power regulator circuit. In conclusion, the fuzzy logic controller was the most interesting of all the controllers, and I was really impressed by how well it worked in varying conditions. If I decreased the speed, it performed really smoothly. I also learned a lot about programming in C. I used structures and modular programming for the project, and the car project was a lot of fun. Some future possibilities for this project might be to add a video camera tracking program. This image is of a video tracking program that is tracking the red LEDs on the car. It places a yellow circle on them. The position of the circle is displayed on the left-hand side of the screen, and the program was made using OpenCV for Python. This concludes my presentation. Thanks for watching.